Imagine looking up at the night sky knowing Earth orbit is an industrial harbor, not an empty void. Giant telescopes assemble in weightlessness. Tankers shuffle propellant between depots and crews board interplanetary ships like ocean liners. All of it driven by a single architecture Starship, acting less like a rocket and more like a freight railroad for space. On Beyond Delta Phi, we are going to unpack how Starship plus orbital refueling could quietly industrialize near-Earth space over the next 2 decades. To see that future clearly, we first need to understand what makes this vehicle fundamentally different from any rocket before it. Starship is a fully reusable 2-stage system, Super Heavy booster plus Starship upper stage designed to launch, land and fly again. At roughly 120 meters tall and 9 meters wide, it is larger than Saturn V and absolutely dwarfs Falcon 9. In fully reusable mode, SpaceX targets around 100 to 150 tons of payload to low Earth orbit in a single flight. Its pressurized payload bay has over 1,000 cubic meters of volume, comparable to the cabin of a wide-body airliner. Underneath, 33 methane-fueled Raptor engines drive the booster, while 6 Raptors power the upper stage using liquid oxygen and methane. Methane burns cleaner than kerosene, allows deep throttling, and can be produced on Mars via in-situ resource utilization, closing the loop. But the real revolution is not just size or propellant, it is the design philosophy, mass production, and airline-like operations. SpaceX wants a fleet of Starships launching, landing, reflying, and improving rapidly, where each vehicle is just another unit in a production line. If they can push per-flight costs into the single-digit millions, or lower the price per kilogram to orbit collapses by an order of magnitude. At that point, Starship stops being a rare flagship rocket and becomes the backbone of an orbital logistics system. Traditional rockets are single-shot trucks. Everything needed for the mission must ride up from Earth on that one vehicle, including all propellant. That constraint forces brutal trade-offs between payload and fuel, especially for high-energy missions to the Moon, Mars, or beyond. Starship sidesteps this by turning refueling into a core feature, not an afterthought, using tanker variants to top up a vehicle already in orbit. A cargo or crew Starship launches mostly empty of propellant, reaches low Earth orbit, then waits while a series of tanker flights fill its tanks. Once full, that same spacecraft can head for lunar orbit, Mars transfer, or deep space with performance far beyond any expendable launcher today. This is the cheat code on orbit. Refueling transforms Starship from a big rocket into a stageable spacecraft platform for the entire inner solar system. If refueling works reliably, Starship becomes an orbital truck fleet instead of a one-off heavy lift vehicle. Different variants specialize: cargo Starship with a giant payload door crew, Starship with life support, and tanker Starship optimized for propellant volume. Over time, purpose-built depots and reusable orbital tugs join the mix, moving cargo and fuel between orbits without constantly diving back into the atmosphere. Instead of designing every mission as a bespoke rocket plus spacecraft stack planners, book slots on a standing orbital logistics network, the cadence could shift from a handful of launches per year to weekly or even daily operations once production and infrastructure mature. With that kind of throughput, the cost per kilogram drops enough that entirely new payload classes become realistic. Instead of squeezing satellites into cramped fairings, designers can think in terms of shipping containers, machine tools, and prefabricated modules. That is where orbital shipyards enter the story, using Starship capacity to build structures in space that would never survive launch from Earth. In microgravity, size is cheap. You are no longer constrained by aerodynamic loads or fairing diameters, only by how many launches you can afford. Starship can deliver heavy equipment like robotic arms, large 3D printers, and machine tools, allowing true fabrication and assembly in orbit. Next-generation telescopes far larger than James Webb could be launched as segmented mirror panels and backbone trusses, then assembled with robotic precision. Rotating habitats for artificial gravity become plausible when each Starship can haul dozens of tons of structural beams, water tanks, and shielding. Inflatable modules launched compactly inside Starship can expand into large pressurized volumes, forming hotels, laboratories, and industrial workspaces. Dedicated dry docks in orbit could host deep space vehicles that never touch atmosphere, nuclear-powered tugs, reusable Mars transfer stages, and more. Instead of discarding entire satellites, operators might send up service missions to swap instruments, extend trusses, or upgrade power systems. The International Space Station gives us a small taste, 420 tons assembled over decades, but Starship changes that scale completely. A single, fully loaded Starship could deliver a quarter of the ISS mass, meaning a comparable complex could be launched in under 10 flights. To keep that orbital industry running, you need fuel depots, the space equivalent of gas stations and shipping ports. A cryogenic depot stores liquid oxygen and liquid methane for months, using sunshades, insulation, and radiators to minimize boil-off. Fluid transfer in microgravity is tricky. Propellants slosh and stratify, so pumps and settled burns help coax liquids into the right tanks. Boil-off without mitigation can reach several % per month, so active cooling with cryocoolers may be needed for long-duration storage. The first depots will likely sit in low Earth orbit fed by tanker starships launching from Earth and refueling outbound vehicles. Later depots at Earth-Moon Lagrange points or lunar orbit become nodes in a CIS lunar supply chain, linking Earth industry to lunar resources. Eventually, oxygen and maybe methane produced from lunar ice or asteroid material could flow uphill to these depots, reducing dependence on Earth. With fuel available on orbit, smaller specialized vehicles can shuttle between depots, factories, and habitats without hauling huge tanks from the ground. What does this mean economically? Launching mass stops being the dominant cost, so hardware design and operations start to matter more than kilograms. If Starship can reach under $10 million per launch and 100 tons per flight, you are approaching $100 per kilogram. At that level, new business models appear: orbital manufacturing, tourism, large constellations, and even data centers, leveraging cold vacuum and abundant solar power. Microgravity manufacturing experiments on the ISS already show promise for exotic fibers, pharmaceuticals, and alloys, but have been volume-constrained and expensive. With cheap bulk lift, entire orbital factories could be dedicated to fiber-drawing crystal growth or semiconductor processes tuned for weightlessness. Space tourism shifts from rare suborbital hops to multi-week stays inside large habitats complete with views, gyms, and dedicated research zones. We might even see power-beaming stations, huge solar arrays in orbit, transmitting energy to rectennas on Earth or other space assets. So, how quickly could this unfold over the next 20 years, and what are the key milestones along the way? In the near term, 0 to 5 years, the priority is making Starship reliable, achieving orbital flights and routine booster recovery. We should see early on orbit refueling demos, short-duration propellant transfers between two spacecraft to validate plumbing and control. Large single-piece payloads will ride first huge satellite station modules and bulk cargo for lunar missions, including elements of the Artemis program. In the 5 to 10-year window, operational refueling for lunar missions becomes likely along with the first prototype fuel depots in LEO. We may see early orbital construction projects, larger commercial stations, multi-module telescopes, and simple dry docks for assembling vehicles. By 10 to 20 years, a mature depot network in low Earth and CIS lunar space could support regular cargo runs and permanent orbital industry. True orbital shipyards might assemble interplanetary ships on a production schedule, while experimental lunar ISRU begins feeding propellant into the network. Of course, none of this is guaranteed. There are serious technical, financial, and regulatory hurdles between here and that industrialized orbit. Making both stages fully reusable with rapid turnaround is hard. Every refurbishment minute and replaced tile eats into cost savings. On orbit, refueling of cryogenic propellants has never been demonstrated at the required scale, and long-duration depots push thermal engineering limits. Robotics and autonomous assembly must advance significantly to handle complex construction tasks safely, far from constant human supervision. Then there is orbital debris and traffic management. A busier low Earth orbit increases collision risk and demands stricter coordination and cleanup. Regulators will have to grapple with safety, launch cadence, spectrum use, and even property rights for off-Earth resources. Competition is heating up too. NASA backs Starship for Artemis, but also flies SLS, while China pursues its own super-heavy Long March concepts. Europe, Japan, and emerging space nations are exploring heavy-lift vehicles, commercial stations, and resource missions, each with different timelines and priorities. The race is not just to plant flags on the moon, but to control the ports, factories, and logistics chains of near-Earth space. Even if Starship misses its most aggressive targets, the direction of travel is clear. Cheaper mass to orbit enables more infrastructure, which enables more missions. The details of who builds which depot or station may change, but the logic of an orbital logistics backbone is robust. So, when you watch Starship test flights, remember you are not just seeing a big rocket, you are seeing the first draft of an orbital economy. If we get Starship-scale full reuse and reliable refueling, the quiet result could be shipyards, depots, and factories ringing our planet. Earth orbit would stop being a distant frontier and start feeling like the harbor district of a much larger human civilization. The real question is not whether we can build this network, but how responsibly we will manage it once it exists. On Beyond Delta V, we will keep following the engineering, economics, and policy shaping this orbital industrial revolution in real time. If you want to understand what happens after Starship works, not just the test flights hit, subscribe and join us for the journey.